Okay, let's take a look at the lab today. Again, it's just covering basics, so it's pretty straightforward. So today we are going to build an inverter, starting with schematic and then layout, and then consider the size of width and length ratio of the inverter of the PMOS to NMOS. We are going to improve the driving capability, but the inverter will be used as it's like a buffer in the future VLSI design circuits. So buffer means if you add more, like two inverters or even number of inverters, it's actually not inverting the signal, it's inverting back and forth, eventually giving you the same signal. But however, since you have more devices in the middle, it has more routes to VDD and ground. So it's actually increasing the width of the diameter of the pipe. So you are able to charge and discharge the capacitor or folding circuits more efficiently. So if you look at this one, the schematic, first you grab the transistors. They can probably notice that there's no fourth terminal, so there's no body contact, because by default, I think either in this lab or the previous lab already told you how to set up the wire contact, N wire to VDD and P wire to ground by default, so you don't have to do that individually, right? And set up the width and length. Remember what is the unit over here? It only shows the numbers. There's no unit, right? Is that 20 micron, 20 nanometer, 20 nanometers? Are you sure electric VLSI can do that?
Oh, isn't that 20 times 300?
Yes, 300 what? Nanometers. So 300 nanometers is 1 lambda. Okay. So 1 lambda. So lambda is a unit. You can see that the length, right? The length. We always use 2 as the length. 2 lambda. And that makes a lot of sense because 2 lambda is 600 nanometers, right? And 500 nanometers is the smallest length the foundry can fabricate. However, we don't want to directly use 500. We want to use a little bit more, a little bit bigger, so it's improving the yield. But do you know what's the most popular technology node currently on the market? Digital circuits wise, it's actually 28. It's actually 28. Even though they can do TSMC can do 2 nanometer or 5 nanometer. So 5 nanometers was 2 years ago, and now they can do 2. So at the minimum length, right? It's just like several atoms, and but the thing is, it's super expensive. 2 nanometer type. If you fabricate a prototype with TSMC at 2 nanometers, it's probably like $5 million. But 28 nanometers is still doable. 28 is still doable. So a lot of startups in the U.S., including China as well, say so if they want to prototype a digital circuits, so 28 is still very popular because it's not too expensive, but also it's pretty advanced node. It's probably 5-year-old, 7-year-old technology, still pretty good. And we're doing 500. And TSMC 180 is $6,000 for 20 copies. That's what our students can do actually, and that's the only one, as I know in the state are doing this actually. It's $6,000. We, for example, if we give you, it used to be $1,000 per student for senior sum, but now they reduced it to $750. If you got 7 people, if you can do the math, right? 7 people is about 5,000 or something, and I can probably, give you guys another $1,000 so we can get a chip fabricated next year. Okay, let's do that here in senior sum. So 2 as the minimum length, 20 as the width. Definitely you can use 2 for the width as well, but 20 is making it a little bit wider, so you can run more current into it. Okay. So this is pretty easy. Build an inverter. Like I said, for this circuit, it's still just 1 layer, right? 1 layer means you just have 1 transistor level circuit and wrap it into a symbol, and we don't have another upper layer circuit. Just for example, if we need maybe 10 inverters for another layer of the circuit, just one thing you need to know. You can see I don't have a connection for VDD and ground. But however, you can assume that at the upper layer or higher level of the circuit, you wrap it with multiple layers, but eventually the VDD and ground are still exported to that layer. Remember I told you guys that? Because since we know a lot of times the ground is a universal ground, the VDD is a universal VDD, right? So we don't want a lot of connectors at the symbol, and it's gonna make the circuit pretty massive, right? So we just assume that VDD, ground and VDDs are like global exports. If you put it in the very bottom layer, they will be automatically exported to the upper layer. You don't have to add a port for VDD and ground. Make sense? But for if you are doing this in LT Spice instead of electrical VSI connecting to LT Spice, you don't have to export it. However, if you are doing this for LT Spice only, I believe you need the VDD, the ports to be exported. Just let you guys know. Because we are doing a DC sweep, so the x-axis is going to be voltage, and y will be voltage as well. So we are looking at the switching point. So we do a DC sweep. This is called DC sweep in Spice. Dot DC, V in 0 to 5 and 0.001. You plot a point. Okay. So eventually this is the x-axis, and here's a linear V in, and there's the V out. That's the switching point. Mm-hmm. They're overlapping with the frame, but you can see the black one is doing this, the black oscillation, and the purple one is just inverting that signal. Okay, but it's two square wave series of square waves overlapping with each other a little bit. And here's the layout. What are these? What is this? What's the name of that component? This is NMOS, right? So what is this? P-tap, right? P-tap. Because NMOS need a P plus. Forgot that. So NMOS need a P-tap, right? So it's a well tap. So P sub is the P well, even though it's not really a well. It's the whole wafer is the well. P sub. So this is the P plus. Oh, sorry. Yes, it's a P sub. And the one on the top is N plus. It's N well, right? Or N tap. Because the PMOS is being fabricated in N well. So the dots, here is the N well. Right? And the slashes here is the P well, or P sub. Even though there's no really physical P well, but it's a P sub slashes. NMOS, PMOS. And in the future, we'll build a bigger circuit. All the PMOS are on top in the same N well. All the NMOS are in the same P well. That's how we organize it. And you don't want to have a PMOS here, another PMOS over here, down here, right? That's not the way we design the outside circuit. So if you have this, it's going to be the whole row will be just one N well, just one N well, one big N well with all the PMOSes over there. So this is one single gate. All the NMOS are at the bottom, okay? And this is P plus, and that is why we connect it to ground, because the P, I think the component's name in the electrical VSI library is called P well, because it's a P well tap. They just name it P well. And it already has a metal one layer overlay on the top and with the vias. So it's actually it's a P plus layer with vias and metal one. That's the component in the library, available in the library. So in that case, because you already have that metal one, and you can directly right click and connect this one to ground, because it's metal one, right? It's a metal. Same to here, connect to VDD. And this is a poly to metal one connector. And this is the output. It's just the metal one because all these two are P plus and N plus has the vias to metal one. You directly connect these two with metal one and then have a little wire here and export it to as out. So V in, V out. Okay, that's the inverter. Pretty classic. Remember, yesterday in the lecture we covered this structure. Oh, it's probably better just show you the notes. Remember I showed you this? This one?
Yeah.
And this one, you can have 2 or 3, 4, 5, doesn't matter. So if you make it a lot of them in parallel and then you short the gates, then you can consider these parallel transistors as one wider transistor. Okay? It's going to be equivalent to one wider transistor. So the way we do that here, definitely you can draw a lot of them, right? You can draw a lot of them and make them in parallel. But electric VLSI gives an option to make it a little bit easier, which is called a multiplier. Okay, so M equals 5, which means there will be 5 in parallel with this guy, and the gates are shorted together. So even though it looks like it's just 1, but actually the width of this device on the PMOS is actually what? The width, the actual width. 20 times what? No, 5. It's 5 in parallel. Okay? So the width is, single one is 20, so 5 will be 100. So it's equivalent to one PMOS transistor with a width 100 and length is 2, right? Similar to this one. So 10 times 5 is 50. So the actual width is 50 for this case. And sometimes you see an inverter here. Okay, so for the PMOS, you have a width slash a length, right? That makes sense because the transistor has 2 dimensions, the width and length. But what about inverters? You see a number, something slash something. What is that? I mean, inverter has 2 transistors. What does that mean? I mean, just 2 numbers instead of 4. It's a ratio of what? Of the width. Why we are ignoring the length? It's the same, right? So by doing that, we're just assuming, we're just telling people the ratio of the width of the PMOS and NMOS. So if you show an inverter symbol and show a number slash another number, it's actually the width versus the PMOS width versus the NMOS width. Like this guy. So that carries a lot of information. This is telling you which one's stronger, right? Because the wider transistor, it will be a stronger transistor. A stronger PMOS will be able to hold the voltage at the VDD for a longer time. So because this guy is actually wider than it looks, so when we are doing the layout, we need to match it. How do we do a 5 fingers of layout? 5 fingers, right? 5 fingers. So we have one PMOS, NMOS, and you grab another PMOS, but you don't add the P plus and with the V and metal one in the middle, because this one they're going to share. They're going to share that contact in the middle. So you grab another PMOS, you connect the one on the right hand side, and you short the P plus from here to here, and then you select everything here, and then you keep pushing that left arrow to move it closer until it's overlapping. Here is overlapping with the metal one and Bs. See? You make the connection first and then move it. Okay? And eventually it looks like this. And because there will be a lot of overlapping, and so after you move it to here, and then it looks like it's working. So the first thing you want to do is F5, right? Just DRC it before you move forward. The DRC it. There will be a lot of errors, I believe. I mean, as a beginner, so DRC it very often instead of having hundreds of errors until it's too late. And now you can see as the 5 fingers for both, and I got a poly connected because it's basically just one transistor. And can you believe that? This is basically just one transistor. It's just one transistor. It's equivalent to just one transistor. DRC it, LVS it, or NCC it. Make sure that the message window shows all the error free and everything match, and then you do a snapshot and put in the report. And the next task is to improve the driving capability. If you just look at the curves, explain itself. You see, I initially have a 20 versus 10. That's the PMOS width versus the NMOS width. It's 20 over 10. And you can see I'm driving a 100 femtofarads capacitor. No problem. You can see I just have an input. I have a series of square wave, and the output is getting inverted. And there is a little delay. You can see it's not perfectly matching or overlapping with the edge, rising edge and falling edge. But however, you can still tell there's a very minor delay, and which makes sense because it's a capacitor. It has to charge and discharge. If I increase it to 1 picofarad, make it 1,000 times larger, the cap, and you can see it's getting affected significantly because the time delay becomes more significant in this case. If I increase it to 10 picofarads, you can tell this little inverter is not able to drive it. It's oscillating. It's not able to drive it. It's not able to fully charge and discharge the capacitor during this time period or at this frequency. Okay, you can say either the driving capability of the capacitor is too small, or you can say the speed of the circuit is too fast. You need to slow it down. Either way, so you need to improve it. Okay, and then I change the width over length. Width of the PMOS over the width of the NMOS, which is basically the 5-finger one we just developed, right? So we replace it with that one. And driving 100 femtofarads, definitely no problem. Driving a 1 picofarad capacitor, definitely no problem. And driving a 10 picofarads capacitor, even though you see a more significant time delay, but actually it can still drive it. It's still fully charging and discharging at the same speed. Because you have a wider device, wider pipe is able to dump and pump more water during the same time period more efficiently. And that's it. It's just 4 tasks, pretty straightforward. Haven't seen big problem in the past, and so we can get started.